Okay, and so today what we're going to move into is the final method that we're going to come up with for how we do system analysis in the time domain. That's convolution. And this is a topic that you should be familiar with from the continuous time domain when we did this in E228, when convolution was a scary integral. The good news is the discrete time version of it is a bit less daunting. It's a simple summation, but the basic concept behind it is the same. It's just that the mathematics tend to be easier, and our main methods for actually computing a convolution tend to be more numerical than analytical in the discrete time domain. So what we'll do today is go through, again, the philosophy behind convolution, what it means, what it's for, and then specifically, what are the different techniques we have for how we can compute a convolution summation in a discrete time system to do system analysis, particularly how we do many of the numerical methods for computing a convolution. And so that's really the motivation why we're trying to do this, is just as in the continuous time domain, one method that we had for finding the output of a linear time invariant system was through the convolution integral that related the input and the impulse response of the system to the output, as long as the system was relaxed. And we have the same situation in discrete time systems, where if we start off with a relaxed system, we can use a convolution process, which is just a restatement basically of superposition, linearity, and shift invariance, that enables us to take any arbitrary input, decompose it into a collection of unit sample sequences, and then use the convolution summation to come up with the output of the system for that sequence of unit sample sequences using scaled and shifted unit sample responses. This is an operation that only applies to linear, time invariant, or shift invariant systems. And it also requires us to have a relaxed system. We have to have zero initial conditions to apply this technique, because it doesn't give us a way of accounting for the response of the system to initial conditions. We can't do any zero input response computations with the convolution summation. We can only come up with the zero state response of a system if it's starting out relaxed and gets hit with a new input. This is how the system's going to respond. And we're changing the way we do system analysis. We're going to replace the difference equation as our system descriptor with the unit sample response. That's going to be the mathematics, the model, if we will, for our system that gives us the information we need about the dynamic behavior of the system. Now, we've been working on how do you derive the unit sample response from the difference equation. So all the information is there. It's basically a packaged form of the natural response of the system, but it's a particular one in that it's the response of the system to 1, 1 at n equals 0. And that's what's going to enable us to use that to compute the general output for any input signal that we can describe as a collection of unit samples that are scaled and shifted. So the idea is, if we put in a unit sample sequence to our linear time invariant system, whatever comes out, we'll call the unit sample response h of n. And we know, because it's a linear system and a shift invariant system, that if we delay that unit sample by 1 or 2 or 3 samples, the unit sample response is delayed by the same amount of time. That's the property of shift invariance. And if we take a unit sample input and scale it by some value, we do nothing more than scale the unit sample response by the same value. That's what linearity gives us through homogeneity. And if we combine those operations and we scale and shift the unit sample sequence, we simply equally scale and equally shift the unit sample response. And so that's putting the properties together. And then the other part of linearity is additivity, that says if I add up a number of unit sample sequences, I add up their responses. So if we take any arbitrary input signal, any discrete time signal is going to be just a collection of sample values. And we can always rewrite that as a collection, a sum of a number of unit sample sequences, where we get one sample each for each sequence, covering one particular index value of our original function. And in order to get back our original x sub n function, we simply need to scale those unit sample sequences by the sample values that occurred in the original signal at those corresponding positions. And so we can write a simple summation formula that describes any discrete time input as a collection, a sum of shifted unit sample sequences that are scaled by one value of the original sequence. And we know that each of these unit sample sequences are going to kick off a unit sample response, a h of n response. And if we've scaled the delta sub n by some value, we scale the h of n by some value. If we delay that unit sample by some number of samples, we delay the unit sample response by the same. And so by decomposing the input into this collection of scaled and shifted unit sample sequences, we can describe our output similarly, because it's a linear and shift invariant system, as a collection of equally weighted, equally shifted unit sample responses. And that is in fact the convolution summation and the concept behind it. It's really just a restatement of linearity and shift invariance. So if you know h of n, if you know the unit sample response, and you have a relaxed system, we can compute the output, y of n, for any input signal, x sub n, using this convolution formulation. And that is the sum that we call the discrete convolution. Has the same conceptual meaning as the convolution integral in continuous time systems, just adapted to this sample-wise world in which we live with the discrete time systems. And it's such a fundamental operation, we give it its own operator, the star operator. When we see that, it means to us that we've got a convolution, in this case, a discrete time convolution that we're trying to carry out. Again, I want to emphasize that the output that we can compute here, y of n, is a zero state response. This will give us the output of the system if we are starting with a system that's relaxed. Okay, but again, we can always look at this convolution summation and remember what it means conceptually. It's based on this idea that if we could describe any arbitrary input signal as a collection, a sum of weighted and shifted unit sample sequences, where the weights actually come from the sample values of the original signal, then the output is nothing more than a sum of equally weighted, equally shifted unit sample responses, because it's a linear time invariant system. And that's all that this convolution summation is saying mathematically to us. How do we compute a discrete convolution? Turns out there's a number of different numerical methods and a few analytical methods that can do this for us. These are methods that are best suited to finite length signals, although I can use them for infinite length signals as well. The issue is, for a numerical method, is what I'm going to get as an answer is a numerical answer. I'll get sample values of the convolution result. And for a lot of situations, that's sufficient. What I won't have is a closed form analytical expression, some function of n, to describe my y of n. For that, I need to apply an analytical method. And we'll go through one example to show how that's done. It's rare to come up with many good situations where we can get an analytical solution, because they involve having summations that we need some kind of known formula for the sum of some kind of geometric series. The numerical methods, though, are very handy, and they come in a couple different flavors. The first is the sum by column method, which is a table-based method. And it has an offshoot called the lattice method, which is just a more compact way to do the same operations implied by the sum by column method. And then there's another, takes the convolution sum and interprets it slightly different from a more mathematical standpoint. And that method is called the sliding strip method, or the flip and shift method. And that's one that's shown in the free textbook that we have for the course. We'll show you how to do a convolution with MATLAB. Turns out to be pretty straightforward. And we'll show you an analytical method for doing it as well. So first method is the sum by column method. And if we look at the convolution sum and just start writing out terms, the terms implied in the summation. And so if we write this up and start maybe at k equals 0, we would have an x of 0, h of n minus 0 term. Then for k equals 1, we'd have x of 1 times h of n minus 1, and x of 2, h of n minus 2, and so on. And we might have an infinite number of these terms. Potentially, we could go infinitely in both directions in general. If our x of n, though, is a causal signal, then this term is going to be 0 for k less than 0. So if you have a causal signal, we would start the summation at n equals 0 and go forward in time. If you have a signal that's not causal, then wherever x of n starts, wherever its first non-zero sample is, that's where we would start generating terms from this summation. The sum by column method basically looks at this summation and creates a table to do this computation, to compute this summation. So first we do is create each of these terms, the x of 0, h of n minus 0, the x of 1, h of n minus 1 term, and each of those gets a row in the table. Then we position them within the table. What columns their sample values appear in are set by the various delays that correspond to each of these terms. So we shift them to the right position to agree with the shifts implied in these different terms in the summation. And then we literally sum by columns. We sum the columns of the table to get each of these rows, pull them all together, and get a single value for each index n of our output signal. So basically what we're doing is we're in a table form doing the operations that are implied by the convolution sum. We're taking first the response of the system to one of our inputs, the x of 0 input creates an x0 times h of n. So we give that a row. And then the x of 1 times delta sub n minus 1 creates an x of 1 h of n minus 1 term. We'll give that a row, but notice it starts us one sample later because of this additional shift. So we move it over one place in the table, and so on until we exhaust combinations of our input signal and our unit sample response. So again, this is where having one or both of these being a finite length is very helpful. Once we have filled in all the cross combinations that are in that summation for the convolution sum, then we do literally sum all the contributions at each index position and get the total response or total value at each instant in time. Now, if you're working with non-causal signals, then we need to pay attention and be careful about these values coming out of the table, relating them to what index n do they belong to. And for that matter, when we're creating a sum by column table, we need to know how many columns am I going to need. The answers to both those questions come from looking at our two original functions that we're going to try to convolve. Here I have two finite length sequences that are both non-causal. Here's my x of n. I've underlined the 7 sample value here, indicating that's my n equals 0 point. And so I have a sample at n equals -2, -1, and 0 for x of n. My h of n has an n equals 0 here at this sample value 4. So it starts at n equals -1 and goes 0, 1, 2. In terms of when I first get the answer out of the convolution from the sum by column table for this first column, what index does that relate to? what I need to do is find my starting index for the answer based on the starting index of the input signal and the starting index of the unit sample response. What do we mean by that? So here's our x sub n that we said has index 0 here at sample value 7. The signal is 0 until we get to this 5. Well, that 5 is at index 0, -1, -2. So the starting index for x, meaning that where does the non-zero part start, starts at n equals -2. Likewise for h, here's my n equals 0 position. The non-zero part starts at n equals -1. If I add the starting index of x to the starting index of h, -2 and -1, I get the starting index of the convolution result of y of n. So my first column here is going to be n equals -3, and then we just count up from there. Next column will be my y of -2. The next one will be y of -1, then y of 0, y1, y2, and so on. So we get the starting index for what our first answer coming out of the table is, what index that applies to for my output y of n. We get that from this adding the starting indices of our x and our h. In terms of how many columns do we need in our sum by column table, well, that depends on the lengths of the individual signals, the non-zero lengths of them. How many samples do they have between when they start and when they go back to 0? And it turns out the number of columns we need, which is also equal to the non-zero length of the output of the system, the convolution result, is the length of the non-zero part of the input signal added to the length of the non-zero part of the unit sample response -1. So, for example, our x sub n, we have 1, 2, 3 samples that aren't 0, so length of x would be 3. H has 1, 2, 3, 4 samples that are not 0, so the length of h would be 4. We would add 3 plus 4 minus 1 is 6. So I need 6 columns of my output to generate all the non-zero values of the convolution result. So if they're starting at -3, they'll be from -3 to +2. The usual way we'll carry this out is pick one of the two signals. Usually we'll pick the longer one and put that across the top, starting at its first non-zero sample value. And if we need any extra values to cover any additional columns, we'll just fill them in with zeros. Then down the side, we'll put the sample values of the other signal, the non-zero sample values. And then here's how we proceed. First, we start with h of n. We're going to multiply it by our x sub n value. We're going to start in this first column. So we'll take 5 times 1, then do 5 times 4 in the next column, 5 times 3 in the following column, 5 times 2, and we could do the zeros explicitly as well and put zeros in here. Then for the next row, we're going to take this value of x sub n and multiply it by our h of n, but we're going to shift over the starting position one place. So we're going to compute x1 of times h of n minus 1. So we want to shift it over one place. So we'll do 6 times 1 and put the answer here. Then 6 times 4 here, 6 times 3, 6 times 2, and continue on with zeros after that. And just keep going till we run out of samples of our x sub n. The last one is 7, so we'll do that. 7 times 1, and 7 times 4, and 7 times 3, but starting one column further over. And just keep going till we run out of one of our signal values. Once we've done that and got all the possible combinations, then we literally, as the name implies, sum by column. Add up all the values in each column. 5, then 20 plus 6 to get 26. And then these 3 values give us 46, and so on. And these are the convolution results. The y of n, the output of the system, if this was my input and this was my unit sample response, here's what would come out. Here's what the result of the convolution is. And our indices that we found from the start indices tell us where to position them. So here's my n equals 0 term of y, and we're starting at y of minus 3. Okay, so it's pretty straightforward. Just got to set up the table right, figure out how many columns you need from the lengths, put one of them across the top, do the other down the side, start in the upper left corner to put the first row, and then just keep shifting one row in between. One little sidebar to be careful of, if we, for example, we had a 0 in between a couple samples here, 5, 6, 0, 7, for instance, we do count and include that 0. I would keep it in my sequence down the side here. I would count it in the number of samples in the length. If it's surrounded by other non-zero samples, we count that as part of the whole signal. We only throw away zeros that are at the leading edge and trailing edge. Okay. Any questions on that method?
Professor, got a question.
John.
Could you explain why, since I thought h of n, the 4 being underlined means like that's the 0th term.
Right.
So I was wondering why that was lining up with the n equals -2 column instead of the 0 column.
The h of n. Oh, over here?
Yeah, like why is that lined up? If you see the n at the bottom, it says negative.
Right, because this n applies to the output signal, not to the h of n. So it was important. So when we're setting up the table, it's important to put the first non-zero sample of h or x, whichever one you're putting across the top. Put that first non-zero sample in the first column, and then the rest following it. This index that we figured out from this formula refers to the index of the output signal, the y of n. But you're right, for h of n, this would be index -1. Okay.
So the reason why it starts at -3, I see that you have n start equals x start plus h start, so that's why we start the output signal at -3.
That's why the output begins there. Yeah.
Okay, I got it. Thank you.
Yeah. So what you're going to see in general with these convolution results, well, we can see it here. The result of the convolution is always longer than either of the two original signals. In fact, it's the sum of their lengths -1. And so it tends to stretch things out. And if you didn't start at 0, it's going to stretch it back in the negative direction as well as the positive direction. And so that's why we need this formula to tell us the first value that comes out of this, what index is that going to end up at? Okay, so that's the sum by column method. Really closely related to it is the lattice method, which is pretty much exactly the same as the sum by column method, except we're not going to shift over each of our terms here. We're going to create them all in a single column. So we'll put maybe h across the top and x down the side, or x across the top and h down the side, whichever way you want to do it. But I don't need so many columns. And I then just multiply the x value times the h and put that in a row. The next x value times the h, put that in the next row. So all the rows line up on top of each other. Now I still need them to add up the way they did in the sum by column method. So what I do is do diagonal sums. You start here in the upper left corner and create a diagonal across the first element, and sum up everything that the diagonal hits. In this case, only one sample value. Then we move over to the next cell and do a diagonal across there. We pick up 2 terms. We get the 20 and the 6, the 26. Move over to the next one, make a diagonal. That gives us 46, and just keep doing that. So basically, we're using the diagonals to do what the column shifts were doing for us in the sum by column method. This is a bit more compact, though, and as long as you draw your diagonals right, you'll get exactly the same answers And all the same rules apply. We know the starting index here for this first one coming out of the first diagonal is governed by the same rule. N start is X start plus H start. So this is index -3 for our output. And the length still comes out to be the same, governed by the same rules. We're just getting them by coming around and continue to create diagonals until we run out of elements that aren't touched. So it really is literally the same as the sum by column, just a more compact way to execute it. Okay. So here's a chance for you to try one and make sure you kind of understand the method. You can use either the sum by column or the lattice method, but try this short exercise in your notes right there. If you have an x sub n signal that has 1, 0, -2, and you're going to convolve that with an h of n that's -2 followed by 7, set that up in the column in that slide, see if you can come up with a quick answer for what that convolution result would be. I'll give you a couple seconds to work that out, and then we'll compare notes here. So you can choose either one to go across the top and one down the side. I usually choose the longer one to go across the top. It doesn't matter, they're interchangeable. We're not going to leave out the 0. That's a term that we need to keep in our convolution. If you use the sum by column method, we would multiply our x sub n by -2 in the first few columns. Then we would multiply x sub n by 7 and shift it over by 1, total up the columns. And our start index for x looks like -1. Our start index for h looks like 0. So this first term is going to be starting index -1. And the length of x is 3. You have to count the 0. The length of h is 2. So 3 plus 2 minus 1 gives us an expected length of 4. 1, 2, 3, 4 non-zero samples. And any after that are going to be 0. That's the sum by column and the lattice method. The next method is really looking at that convolution sum and the mathematical statements that it's making, the mathematical operations that it's implying. So I'm going to come at and get to the same place, but by a slightly different process. We haven't proven this. We'll work on that next time to show that, but the convolution operation is commutative. Meaning if I convolve x with h, I get the same answer as if I convolve h with x. So basically, it doesn't matter which one of these two I make my n minus k and which one I make just the k. I get the same answer. Now that's helpful. That means I get to choose which of my two functions I'm going to be shifting around and playing around with. And usually we'll choose the simpler of the two. The sliding strip method, though, looks at either of these two equations and said, oh, well, there's some mathematical operations that are implied here that we should take into account, and that we can just follow through those individual operations and see what we get as a result. And this method, sometimes called the flip and shift method, looks at these and says, okay, over here on the right-hand side of my equation, my independent variable is k. I'm doing a sum over k. So x of k, well, that just looks like x sub n, and I've changed my variable to k. Nothing surprising there. But this h of n minus k, I have to rethink about which one's the independent variable, which one represents a time shift, what's the operations that are implied here. What the summation is saying, for every individual value of n, for every index I want to compute, I'm going to be modifying this summation by changing the n here. And that n implies, if k is my independent variable, n implies a shift, an index shift, a time shift, if you will, in my h signal. And the thing I'm shifting is not k, a function of k, but a function of minus k, a flipped version, a time reversed version of the signal. And so these operations together imply a reversal and a shift, a flip and a shift. And the equivalence of these two says I can choose which of the two signals I want to flip and shift. I get to choose them, but I only get to do it to one. And for every index of the output that I want to compute, I've got to shift this h by a different amount. So I choose one, flip it and shift it. Then I have to multiply that flipped and shifted version of the signal by the other signal. And by multiply, we mean multiply them sample by sample by sample, line up their indices and multiply them at each index position. And then total up all of the sample products that we got to come up with a single value that I assign to y at the index position given by whatever shift I applied here when I did the computation. That's way too many words. We need some pictures. So it's still sort of falling into the same approach, the same idea of convolution as a sum of weighted and shifted unit sample responses, but it's more looking at if I want to figure out what is y at one particular value, well, I'm going to need one value out of this combination. I'm going to need another value out of this combination. I'm going to need a different value out of this combination where my h has been moving over each time. And so I'm creating the sum, getting all these values added up together. Or a way of looking at it that more matches the way we describe the mathematics, this flipping and shifting operation, is that if y of n looks like this, and I want to create this convolution sum, well, if h of n looks like this, h of k looks identical to this, just change the index from n to k, but has the same sample values in the same position. I need x of n minus k, where k is my independent variable. Here's x of n. X of k would look just like this, except trade the n for k. X of minus k, though, looks like that running backwards. So instead of going 1, 2, 3 in the forward direction, I go 1, 2, 3 in the reverse direction to the negative index range. And then x of n minus k is this shifted to the right by n. So if I'm trying to compute y at n equals 0, I will shift this over by 0. I'll leave it where it is. Multiply my h of k by x of 0 minus k, sample by sample by sample by sample. In this case, all the samples multiply out to give me 0 values. And then perform the summation, add up all these sample values to get one output sample value at index 0, which matches the shift that I applied to my x here, and get my answer up there, y of 0. Then to find y of 1, the next output position, we take our x of 0 minus k and make it x of 1 minus k. So shift it over to the right by one place. Now multiply these two, sample by sample. And now I have 2 times 0, but I have a 1 times 3 here at position 1. So that leaves me one sample value with a height of 3. Add them up, add all the ones in this product. I just have a 3. And that becomes my y of 1, the index 1, which matched the shift that I applied to my x. One more, we'll do n equals 2, so we see a little bit more overlap. To find the next output sample at n equals 2, I'll shift my x to minus k plus 2, move it over one more place. Multiply all the x's times the h's. I get 0 times 3, I get 4 times 2, gives me 6, 4 times 1. Add up all these terms, I get 6 plus 4, 10. So y of 2, the amount I shifted, and here at index 2 is 10. And I would just keep doing that. That's literally a mathematical interpretation of the convolution summation. As you can see, it's a lot more cumbersome. It's a lot more tedious than the table method, but it will give you the same answers just by a different process. So for numerical answers, probably one of the first two techniques, the sum by column or the lattice method, might be preferable. The flip and shift or sliding strip method will give you the same answer. If you want to compute it numerically with MATLAB, well, it turns out MATLAB does have a convolution function. It's a CONV function where we give it two array names separated by columns, and it will give us the sample values of the convolution result between those two vectors. So for example, if we did the one that we did in the previous table example, x was 1, 0, -2, and h was -2, 7. So we define those arrays in MATLAB, tell it to convolve those and set that equal to y. It would say, okay, y now has values of -2, 7, 4, -14, which is what we came up with doing that by hand. And notice we had 1, 2, 3, 4, 5 samples going in. So we get 1, 2, 3, 4 samples coming out due to the lengths. And MATLAB doesn't keep track of indices for us. It's kind of assuming that your first index here is, well, in MATLAB lingo, that's at index 1. Everything's at index 1 in the starting position. But we would have to use our X start and H start to figure out what is this starting index for this first value in our array coming out of MATLAB. But it will do that computation for you. So we've got several numeric methods: the sum by column table method, the sliding strip method, the lattice method. We can use MATLAB. What if we really, really needed some kind of analytical answer, some function of n that describes our output? How would we get that? How would we approach that? Well, here we're going to be modeling the method that we might use, similar to doing an analytical approach with the convolution integral in continuous time systems. Let's take an example. Let's take two functions, and two that aren't quite so well suited to doing by the numerical methods because these are infinitely long sequences. So I have an IIR system unit sample response, an infinitely long unit sample response, 1/2 to the NU of n. And I want to know what is the step response of that system. So I'm putting in a unit step function which starts at n equals 0 and stays 1 forever. So I have two infinitely long sequences that are causal. They both start at n equals 0. So I would need an infinitely large sum by column table to tell you the answer to this convolution result. We're not going to do that, obviously. We can use a table, though, to come up with the first couple of sample values. So let's do that. So we have a basis for comparison of the answer we come up with to analytically. Both of these have 0 values prior to n equals 0. So they both have starting indices of 0. This U of n turns on at n equals 0. So does the one here. So the starting index of our convolution result coming out of this first column is going to be n equals 0. Lengths are technically infinite. Let's plug in the values of h of n. For n equals 0, h of n is 1, then 1/2 to the first, 1/2 squared, 1/2 cubed, and so on. And x sub n, starting at n equals 0, is 1s forever, forever, forever. So this is pretty easy. We just multiply 1 by our h of n. We replicate h of n, shift it over, shift it over, shift it over, and keep doing that. And then sum down each column: 1, 1.5, 7 fourths, 15 eighths, and so on. So at least these first values will be reliable. If I wanted the correct answer for this next one, I would have to add another term down here. I'd need another x sub n row to complete this one. But this is enough to get us started. So these are the values we want to generate with some function of n that we come up with as a result of our convolution. Well, how would that go? Let me switch to a whiteboard here, and let's try to go through this problem. So I'm going to try to plug these two functions, my x of n and my h of n, into this convolution sum and see if we can come up with a closed form answer for it. H of n, it was 1/2 to the n. U of n, we had our input signal. X of n was a unit step. So what does that look like? So it's 0 for n less than 1. Then equals 0, it's 1. Then it keeps halving. It's 1/2, and then equals 1, then 1/4, then 1/8, and so on. And our x of n is a unit step, which we're familiar with. It's 0 for all time prior to n equals 0, then goes to 1, and so on. I'd like to convolve those. So we plug it into our convolution summation to sum over all k from k equals minus infinity to plus infinity of our h of k. And I'm going to choose to flip and shift my x of k. That unit step is a little bit simpler to deal with. And if we write that out, this k goes from minus infinity to plus infinity. Our h of k, if we substitute in k for n, that's 1/2 to the k times u of k. And our x of k is just unit step shifted and flipped with respect to k. Now what do we do? Well, our u of k and our u of n minus k are going to change the limits of our summation there. Right? U of k is going to be 0 for all k less than 0. So when I multiply u of k by anything else, for all the negative values of k, that product is going to be 0. That's going to result in my lower boundary changing to k equals 0. And what about this u of n minus k? That equals 0 for all, well, when n minus k is less than 0, or when k is greater than n. So we take our u of minus k, right? That's zeros and ones going backwards. When we make it minus k plus n, we shift it forward. And then it goes to 0. The last sample there is going to be at k equals n. So in our summation, for any values of k that are greater than n, this product is going to be 0. So we can end our summation at n, not at infinity. And we have our 1/2 to the k. And within these boundaries, both u of k and u of n minus k are both equal to 1. And so now I have a finite sum of a series of 1/2s from k equals 0 to n. And if you look that up in a math textbook, you might find a formula like this: a sum from k equals 0 to capital N of some alpha to the k. It's going to be 1 minus alpha to the capital N plus 1 over 1 minus alpha, as long as alpha is not equal to 1. So for our case, our y of n is going to be 1. I need to subtract our alpha is 1/2. Our big N is little n. We have a 1 minus a half in the denominator. That denominator is just 1/2, which means I'm going to multiply everything by 2. And let me rewrite that 2 as 1/2 to the minus 1 so that I can cancel out this n plus 1. And we get y of n then is going to be, well, the one that goes away, that goes away. 2 minus 1/2 to the n. That started at n equals 0. So our starting index again was 0. And so we have one case where we actually do have a closed form solution. And we can even look at this a little bit more closely. It's 2u of n minus 1/2 to the n u of n. We might recognize this is a forced response, and this is a natural response. Right? I put in a unit step, and got a unit step out. That must be the forced response, leaving this to be the natural response. And we lost a thing there. And if we plugged in n equals 0 to compute what is y of 0 in that equation, it would be 2 minus 1/2 to the n is 1, which is 1, which matches our numerical answer. Set n equals to 1. Y of 1 is going to be 2 minus 1 times 1/2, which is 3/2, and so on. So if we keep plugging in different values of n in here, we'll just trace out those numerical values that we got in the previous case back in the PowerPoint. Okay. So this method works best, most easily if you have two causal signals that start right at n equals 0. Then you'll tend to have these kind of summations starting at 0 and going to n, because the causal signal that you flip and shift is going to put the n upper bound. The fact that they're both causal will give you a starting position at k equals 0. Then you'll have some kind of finite summation, hopefully one that you have a formula you can look up in a textbook to come up with. Those kind of cases are the ones where you can actually get analytical solutions, functions of n, that are a result of our convolution. But for the most part, we'll be using the numeric methods, because if we wanted to come up with this answer, it's actually easier to do it using transforms, just as it is in continuous time. We try not to do convolutions, graphical convolution or analytical convolution in continuous time systems. Instead, we use Fourier or Laplace transforms to perform convolution. It's going to be the same story here in discrete time. If we really needed these analytical solutions, we're probably going to use, in this case, Z transforms or discrete forms of the Fourier transform to come up with those. If I need numeric values, though, we have those table methods. We have the flip and shift method. Do you need to be able to do all of these? I would say for the table methods, for the numerical methods, choose one of them. The sum by column, the lattice method, or the flip and shift method. Get really good at one of those. You want to be able to perform a numeric convolution. But I'm not going to say do it X way or Y way. As long as you can get a appropriate answer, a correct answer by one of the methods, that's good. Be aware of this analytical method and how it works. But as I said, we'll be coming up with better techniques for doing that in the future. Okay, that's how we compute convolution results. Next time we'll come back and look at some of the properties of convolution, some of the ways we apply it, some shortcuts and things that we need to know, and the effect of some special operations like zero padding and zero insertion, and a new kind of convolution that we didn't have in continuous time systems, namely circular convolution, which is something that pops up in discrete time systems that's unique to discrete time systems. So we'll need to see how they work, where they come from, how to compute those, and that'll be on Wednesday.